Hello and welcome back to the course on machine learning. In today's tutorial, we will find out how we can take our non-linearly separable dataset, map it to a higher dimension and get a linearly separable dataset, invoke the support vector machine algorithm, build a decision boundary for our dataset, and then project all of that back into our original dimensions. So quite a lot to cover. Let's get started. First off, we're going to look at a simplified example. We're going to look at a one-dimensional dataset. So normally we visualize everything in the PowerPoint with 2 dimensions to make it look pretty, and so that we can kind of understand how it would work in multiple dimensions. But right now that will be a bit too complex for us to start with. So we're going to start with a single dimension. So here we've got the x1 dimension. We've got some points here, so we've got 9 data points, and as we can see, they are non-linearly separable. So in this dimensional in a single dimensional space, a linear separator would not be a line, it would be a dot, right? So in a 2-dimensional space, a linear separator is a line. In a 3-dimensional space, it's a hyperplane, but in a 1-dimensional space, it's a single dot. So can we separate the green from the red with a single dot here? No, we cannot. If we put it here, then these will be separated from that. If we put it here, it will be separated from that. So this is a non-linearly separable data set. Now, how can we apply the method of increasing the dimensionality of this space to make it a linearly separable data set in a higher dimension? That's what we're going to look at, and it might seem impossible, right? So the first time I learned about this, for me it was like, wow, how can you take a non-linearly separable data set and somehow magically increase the dimensionality and you get a linearly separable data set? That sounded like absurd, but it is actually possible, and that's what we're going to see right now. So we're going to create this mapping function on the fly. So let's say that this point over here is around 5. So this is 0 over here, and then somewhere here we've got 5. It doesn't really matter, it can be any number, but just for argument's sake, let's say that this point over here is 5, right? And then it keeps going. So our first step to build the mapping function, there can be multiple mapping functions that you can build. I'm just going to show you one that came to my mind. So the first step will be to go f equals x minus 5, so to subtract 5 from our data set, and that is going to what is that going to do? That is going to move everything to the left. So basically now this is what the result looks like. So if you take 5, you subtract 5 from x, you'll get, like these ones will go into negative, these ones will stay in positive. And then the next step would be to square all of that. So f is now equals to x minus 5 squared. So how will that all look like? Well, basically you'll have this squared function going through your chart, and then all of these will be projected onto the function. There we go. So that's what it looks like, f equals x minus 5 squared. And now what we want to do is we just want to see that it is indeed linearly separable. So there we go. There's our linear separator. So in a 2-dimensional space, as we remember, a linear separator is a straight line. And as you can see, this data set became linearly separable in this dimension. I know it's surprising and even a bit shocking, but indeed it is the case. So you can see that we were able to take this line and separate all of the red elements of our data set from the green element, and that's it. And then what we would do next from here is we would project everything back onto our original space, and we would know how to functionally separate the green from the red. And that is what happens when you map something to a higher dimension. So now, knowing this example and seeing that it works in reality, we can proceed to a higher dimension, to start with a 2-dimensional space. So let's have a look. So there's our two-dimensional space, and basically you would apply the same principle. So here you cannot invoke the support vector machine algorithm because it is not a non-linearly separable data set in this space. But then you would apply some sort of mapping function. Like right now, we won't go into detail what exactly mapping function it would be, and again, there could be multiple different options and so on. But basically, based on the previous example, we now know that it's possible. Like we've seen empirical evidence that it is possible to do, and the same thing applies to two-dimensional space moving into a three-dimensional space. You would map it into a three-dimensional space, and then somehow it would become a linearly separable data set in this space. And here we've got the new dimension, which is Z, and in a three-dimensional space, the linear separator is no longer a line, it's a hyperplane. And so this hyperplane separates the two parts of our data set in the way we want. So the support vector machine algorithm has helped us build this hyperplane. And then basically, so we've got this result. Then we just project it back into our two-dimensional space, and we've got this circle that encompasses our classes, or separates our classes. And there we go, we've got the non-linear separator. So as you can see, we can still, even though we have got a bit of a more complex problem where we cannot directly apply the support vector machine algorithm as we used to, we can still go into a higher dimension and then apply the support vector machine algorithm. And like we won't go into detail if it's possible all the time, and if there's cases when it's not possible and so on, what you would do there. But the point is that there is a solution that you can explore the higher dimensions, so that this is not a dead end. You can just do that. But there's a problem. There's a problem with this algorithm. And the problem is that mapping to a higher dimensional space can be highly compute intensive. So it might require a lot of computation, a lot of processing power, and the larger your data set, the more of a problem this can cause. And therefore, this approach isn't the best, because you can imagine, like, you have a data set and then mapping it to a higher dimension, performing all the calculations there, and then coming back to your lower dimension. That can, even for a computer, not just like in our minds as humans, but just like for a computer, that can cause a lot of delays. It can cause a lot of like processing backlog and issues in that sense. And we don't want that to happen, and therefore we're going to explore something else. We're going to explore a different approach, which is called in mathematics the kernel trick. And that approach is going to help us perform very similar, gets very similar results, but without having to go to a higher dimensional space. And we're going to talk about that in the next tutorial. It's going to be exciting, and I can't wait to see you there. Until then,